Alright, thanks for watching, and in today's video I will define the real numbers but in a cool way. And seriously, if this doesn't amaze you, then I don't know what will. So, consider the following motivation. So remember, we don't know what real numbers are, so suppose we only know what rational numbers are. And the question is, how would we define pi? Well, consider the following sequence. 3, 3.1, 3.14, 3.141. Well, this sequence converges to pi, but we don't know what pi is. So the question is, how do we define pi? No problem. Let's declare this to be pi. Isn't that amazing? It's where the problem itself becomes a solution. It's kind of like all your life you've been searching for pi, but it's been with you all along. They say, it's not about the goal, it's about the journey. That's precisely we define our goal to be the journey. However, there's only one issue because there are other sequences that converge to pi, like 4, 3.2, 3.15, etc., etc. Well, this also equals pi. But that's not a big problem because we'll basically define those two sequences to be equivalent. So, in other words, pi is just the equivalence class of all the sequences kind of going to pi. But of course we need to formalize this, and for this we use the definition of a Cauchy sequence, which I'll remind you what that is. So, reminder, so Sn is Cauchy if, for all epsilon, there is some threshold, capital N, such that if m and n are after that threshold, so usually greater than capital N, but just to make things easier, let's say greater or equal, then Sn minus Sm is less than epsilon. In other words, again, if you consider your sequence, after that threshold, the values of the sequence are very close to each other. So if this is Sn and this is Sm, they're very close. In fact, they're within a region of size epsilon. Okay, so in particular, what is the real numbers? Is just a set of all Cauchy sequences, but with an equivalence relation. So, and in other words, what we would like to say is two sequences are equivalent if they're eventually very close to each other. So, first of all, let S be the set of Cauchy sequences. In the rational numbers. And now let's define a certain equivalence relation. So we say Pn, a sequence Pn, is equivalent to Qn. Informally, it means that if and only if the limit as n goes to infinity of Pn minus Qn is 0. And what this means, again, formally, it means for all epsilon. In this case, remember, we don't know what real numbers are, so rational epsilon, there is capital N, such that if n is greater or equal to capital N, then Pn minus Qn is less than epsilon. So again, all this means is really Pn and Qn get really closer and closer together. They're just arbitrarily close. And again, that brings us back to our motivation. So for instance, you see, we had the sequence 3, 3.1, 3.14, dot, 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 and also the sequence 4, 3.2, 3.15. Well, in fact, they're equivalent under this definition. So that's why we can define pi to be either of those things. And well, why do I write equivalent? Because first of all, this is an equivalence relation. In fact, squiggle is an equivalence relation. Okay, on S. And this is not very hard to show. For instance, let me just show transitivity. So suppose Pn is equivalent Qn and Qn is equivalent to Rn, PQR, and then show, so in other words, what do we know? And we know that the limit as n goes to infinity of, well, Pn minus Qn is 0. Doesn't matter here if we put absolute values or not. And we know that the limit as n goes to infinity of Qn minus Rn equals 0. And then we want to compare Pn and Rn, then the limit as n goes to infinity of Pn minus Rn, well, that is the limit as n goes to infinity of Pn minus Qn plus Qn minus Rn. And because each of the limits exists, so Pn minus Qn plus the limit of Qn minus Rn, we can have the addition law here, and then this is just 0 plus 0, which is 0. So in other words, the sequence Pn is equivalent to the sequence Rn. And you can show the other things similarly, if not more easily. All right. So we know that squiggle is an equivalence relation, and here's the promised definition of R. It's just the equivalence classes of S with that equivalence relation. So here's a definition. R is just a set of equivalence classes. Of S. Okay? Under this equivalence relation. Now, for instance, as I said, as promised, what is pi? Well, pi is the equivalence class of the sequence 3, 3.1, 3.14, dot, dot, dot. So all the Cauchy sequences that are very close to 3, 3.1, 3.14, and which is also the equivalence class of 4, 3.2, 3.15. And in fact, by the way, this is how you view pi in real life, because say you work on a numerical analysis problem and you have a sequence converging to pi, then you say, well, for our purposes, it's the same as pi. And so that's one thing. And then, well, this is an equivalence class, and the next thing is we want to show that the real numbers are a field with that equivalence class, but it's not very hard to define addition and multiplication. So for instance, the sum of two real numbers, so the sum of Pn and Qn, is just defined as the class of Pn plus Qn. But the only thing you need to show is that this makes sense. It doesn't depend on Pn and Qn, but again, that's not too hard to show. You can do this. And what is a little bit more annoying to show is, well, actually, no, it's with this, it's easy to show that R becomes a field. So you can actually show that all the field axioms are satisfied, but we want to have more. So now we want to define order relation. So we want to show that R is an ordered field, and this is quite interesting. So you would like to say that a sequence Pn is less than a sequence Qn if all the values of Pn are less than all the values of Qn. But because we're having Cauchy sequences, this doesn't mean much. However, what we want is something slightly stronger. Namely, what we want is after the threshold, capital N, not only any value of Pn is bigger than any value of Qn, but we actually want something more uniform. Namely, if you take any value of Qn and any value of Pn, not only is it bigger, but it's epsilon bigger. In other words, the two sequences Pn and Qn, they are social distancing. They're always at least epsilon apart. So, to formalize this, Pn is less than Qn if there is epsilon and there is capital N, such that if m and n are bigger or equal to capital N, then Qn is always bigger than Pm plus epsilon. So again, yes, Qn is bigger than Pm, but really uniformly bigger. So with a factor of epsilon. So Qn really doesn't like Pm. Okay. And then you can also define less than or equal by just saying it's either greater or equal or it's equivalent. Okay, so, and you can check with this relation that R becomes an ordered field. So that's already good. And not only that, because at this point it's not clear that a rational number is also a real number, but we can simply embed the rational numbers in the following way. Namely, if R is in Q, okay, then R bar, we define R bar to simply be the constant sequence. R. And in fact, because that's how you can construct a sequence using just a rational number R, so really R bar is this. And of course it's a Cauchy sequence, so it's completely fine. So again, it's the sequence with constant value R. Think of almost like a constant function in some case. And also, I'll try to not abuse notation, but usually if I ever write Pn, a sequence, is less than R bar, what I really mean is, yeah, that the, that's fine. So again, if I write this, okay, I really mean again that Pn, it's less than the constant sequence R. So again, this is R bar, and then I'm just saying Pn is again uniformly smaller than R bar. Okay, and now, of course, so we've shown that R is a field and it's an ordered field, but the most important thing is now to show that R has the least upper bound property, because it's that what distinguishes the real numbers from the rational numbers. So let's show this. So claim R has the least upper bound property. Why? So what does that mean? So let S be a non-empty subset that is bounded above let's say by Pn, and let's show that S has a least upper bound. In other words, we want to show sort of that the maximum of S exists. there is an optimal upper bound. So again, what is the picture? So what is the scenario? Suppose S looks like this. So the sequences aren't necessarily like that, but just for clarity, assume that they're separated like that, and we know that it's bounded above by this sequence Pn. And what we want to do, we want to find some sort of a least upper bound, kind of like that. That's what we would like to find. And the way we do this, we construct this in steps. So we first define Q0, and then Q1, Q2, etc., etc. Okay, so let Q0 be the smallest integer. Of course, we have to show that this exists, such that the constant sequence Q0, so Q0, 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 perhaps the class, is an upper bound. For S. So what we want to do, we want to find the least upper bound, but just among the integers. So the smallest integer that is an upper bound for S. However, it's not really clear that such a Q0 exists, but let me show you at first intuitively why this exists. Well, Pn is a Cauchy sequence, so it is bounded, and in particular, we'll be able to find an easy integer that's an upper bound for Pn. So this Q0 is an infinity. So that's good. And similarly, it turns out Q0 cannot be minus infinity, because there's at least one sequence that is bigger than an integer. So by the upper bound, it cannot be minus infinity, which really means that there are just finitely many of values to compare from. And remember, for finite numbers, there's no problem of having a biggest or smallest value. It's really for infinite numbers where this idea of sup and inf come into play. So again, this Q0 has to be strictly between minus infinity and infinity, and then just successively check the values until you find one that works. And you know you have to stop because it has to stop at this bigger thing, at least. Okay, good. But now let's formalize this. So let's talk about the upper bound first. So why? So let's talk about Pn. So by definition of Cauchy, and here I'll use a very specific value. So since Pn is Cauchy, if you let epsilon be 1/2 and then n be capital N, whatever that means, there is this capital N such that if n is bigger than capital N, then Pn minus Pn bar is less than 1/2. So again, the upper bound is Cauchy, so it's actually not very far away from its initial value in some sense. So again, this is capital N, this is Pn bar, and so P capital N, and then essentially, because Pn is Cauchy, we know all the other values of Pn are at most 1/2 away. And what's the idea? Well, then Pn is actually just bounded above by P capital N plus 1. And this is not an integer, but then we'll be able to choose an integer that's bigger than it. And that would show that the Q0 is not infinite. So, what does that mean? So, we know that, again, Pn minus Pn bar is less than 1/2. So we can remove the absolute values. And then what we get is Pn is less than Pn, P capital N, plus 1/2. Now we would like to say that Pn is less than Pn plus 1/2, but remember in our definition of less than there has to be an epsilon, but here's how to make the epsilon appear. You just add 1/2. You see, this will be our epsilon in the definition of class being less than something else, and therefore what we get that the sequence Pn is less than the constant sequence P capital N plus 1. So if you want this P capital N plus 1. And therefore, now just pick an integer that's bigger than P capital N plus 1, which you can do, that's not a big problem. And so now pick K such that K is bigger than this value, P capital N plus 1. Again, there's always an integer bigger than a rational number. That's not a big issue. And then, what do we know? So then for all Sn in S, what do we know? We know that Sn, well, it's less than Pn because Pn is an upper bound, but this is less than Pn, P capital N plus 1. But now we also know this is less than K capital, so the constant sequence capital K, and then therefore we know there is an integer at least such that Sn is smaller than that integer. So there's an integer upper bound for your set S. So in particular this Q naught, if it exists, is less than infinity. And similarly, you can also show that Q naught is bigger than minus infinity. So similarly, you can show Q naught is bigger than minus infinity. And how do you do that? So let me just summarize. So pick some Sn, doesn't matter which one, in S. And then basically in the same manner, you can show that Sn has to be bigger than the constant sequence S capital N minus 1. And since Q naught has to be bigger than Sn, well, it's bigger than this constant sequence S capital N minus 1, which is bigger than some integer. You see, this fixed value is bigger than some integer, and therefore, essentially, Q naught exists, because you just have a finite number of values to compare to. Again, if you want to make this rigorous, do an inductive argument. So start with this Sn hat, S capital N minus 1, and then, well, if this doesn't work, go one step above. If this doesn't work, just add it by 1, add by 1, add by 1, and this has to stop because we know everything is bounded above by capital K. So, very good. So we know this is true. And then how do we have to define Q1? Well, the same thing, but this time you're just focusing on fractions with denominator 2. So it's very similar, I would say, in principle to Riemann integration. So let Q1 be such that be an integer, be the smallest integer, okay? The smallest fraction with denominator 2. Again, think 3/2 or -7/2, something like that. Or even, integers, think 4, which is 8/2, such that Q1 bar is an upper bound for S. And similarly, you can define Qn bar be the smallest fraction with denominator 2 to the n. Think like 3 over 2 to the n, such that a Qn bar, so we define Qn to be the smallest fraction with denominator 2 to the n. That is an upper bound for S. And now notice an integer is a special case of a fraction with denominator 2, which is a special case of a fraction with denominator 4, etc., etc. So of course, it turns out this Qn is a decreasing sequence because we're kind of refining our result in some sense. So again, let me illustrate this with a nice little picture. So we have our sequences Sn, and again we chose Q0 be the smallest integer bigger than Sn, and then Q1 it's the smallest fraction, and Q2 it's even smaller and even smaller. So it turns out, yes, the Qn are decreasing. So then Q0 is less than equal to Q1, is less than or equal to Q2, is less than or equal to Qn, etc., etc. And I'm actually claiming, and it seems kind of clear from this picture, what is the least upper bound? Well, it is, strictly speaking, the limit of the Qn's, but we can't really talk about, limits here. However, remember, the problem is our solution, so we literally define our least upper bound to be the sequence Q0, Q1, Q2, Q3, etc., etc. Remember this analogy with pi being 3, 3.14, 3.141, etc., etc. So claim. Then this sequence Qn, which is, again, Q0, Q1, Q2, is our least upper bound. Okay, so what do we need to show? 3 things. First of all, it's not even clear that the Qn is in our set. So we first of all need to show that Qn is Cauchy. Then we need to show that Qn is an upper bound. And lastly, we need to show that Qn is the least upper bound. So claim 1. Qn is Cauchy. Again, that guarantees that Qn is in our set, because we need to show this is a real number. And so let epsilon be given, and then capital N be to be announced. Then, if m and n are bigger or equal to capital N, without loss of generality, assume this is smaller than n. So, one of them has to be smaller than the other one. So without loss of generality, assume m is less than or equal to n. So then, on the one hand, remember your sequence is decreasing. So this means that Qm has to be bigger than Qn. So on the one hand, Qm minus Qn is greater or equal to 0. On the other hand, let's use a telescoping argument. So this becomes Qm minus Qm plus 1 plus Qm plus 1 minus Qm plus 2 plus Qn minus 1 minus Qn. Now remember the definition of, Q0 and Q1. So Q0 is the optimal integer, Q1 is the optimal fraction with denominator 2. So because they're kind of optimal, they can't be more than, I think in this case, they can't be more than 1/2 apart. See? And similarly, Qn minus Qn plus 1 cannot be more than 2 to the n plus 1 apart. Otherwise, we can choose just a bigger fraction with denominator 2 to the n plus 1. That would work. Okay. So in particular, this is, again, by construction, because they're so close to each other, this is less than or equal to 2 to the n plus 1, plus 1 over 2 to the n plus 2, etc., up to 1 over 2 to the n. But you may recognize this as a geometric sum. So this becomes 1 over 2 to the n times 1/2 plus 1/4 plus ... plus 1 over 2 to the n minus n. But just very crudely, we can estimate this with the geometric series. So 1/2 plus 1/4 plus ... which is 1. And that becomes 1 over 2 to the n. And then simply choose capital N big enough such that this becomes less than epsilon. So if capital N is large. Since M is bigger than capital. Very good. And then what do we get? Then we get Qm minus Qn is between 0 and epsilon. So indeed, it is Cauchy. Okay, good. So the sequence is Cauchy. It is, it joined the party if you want. And now we want to show that it's an upper bound. I know, isn't this proof crazy long? But it's okay. We're having fun. So claim number 2. So Qn is an upper bound for S. Well, suppose not. Then it means there's an element in S that's bigger than Qn. Then there is some sequence in S with Qn is less than Pn. But remember, there's this definition, very good definition of less than. So again, this is Qn, and this is Pn. And we know they're at least epsilon apart. So there exists epsilon such that for r large n, what we have is, well, Pn is bigger than all the values of Qn. In particular, it's bigger than Qn bar. So for all n, n bigger or equal to n bar, what do we know? We know that Pn, it's bigger than Qn. Now remember, there is a very specific notion of less than here. We don't only mean that Qn is less than or equal to Pn, but really we mean it's uniformly less than. So in other words, if this is Pn and this is Qn, they're at least epsilon apart for some epsilon. And since this is true for all n, it also means that Pn is bigger than Q capital N. So there is epsilon such that for all n bigger than capital N, we have that Pn it's bigger than Q capital N plus epsilon. But then what does that mean? It also means that the sequence Pn is bigger than the constant sequence Q capital N. But then Q capital N bar is less than Pn. But then what's the contradiction? Remember, we defined Q capital N to be the smallest fraction, blah, 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 that is bigger than any element in S. So again, given Sn, remember we defined our Qn's in general be such that the constant sequence is bigger. It's an upper bound for all the Sn's. And that's why this contradicts really the definition of Qn bar. So this contradicts Qn bar being an upper bound. Okay, so we have that, and then, so it's a contradiction with what? It's a contradiction with it not being Qn, not being an upper bound for S, but now, what do I want to say? But now we need to show that it's a least upper bound. So claim number 3. So Qn, it's really the least upper bound for S. What does that mean? It's a least upper bound. Well, suppose you have a smaller upper bound. So Rn less than Qn is a smaller upper bound, and we want to find a contradiction. So what does it mean for Rn to be less than Qn? Well, this means there is epsilon such that, and a threshold capital N, such that if m and n are bigger than or equal to capital N, then Qn is bigger than Rm plus epsilon. Okay, so this is true for all n, and now, in particular, because we have to have powers of 2, because the denominator has to have powers of 2, let's choose a k large enough such that 1 over 2 to the k, it's smaller than epsilon. So choose k bigger than or equal to capital N with 1 over 2 to the k less than epsilon. And we can do that because 1 over 2 to the k goes to 0, so definitely it's less than epsilon. But then what do we have? Well, since this is true for every m, we have Rm is less than Qk, so Rm plus epsilon is less than Qk, so Rm is less than Qk minus epsilon, but minus epsilon is less than 1 over 2 to the k. So this becomes Qk minus 1 over 2 to the k. So Rm is less than Qk minus 1 over 2 to the k. And it might seem obvious, but what do we have? We have the sequence, Rn if you want. I just showed that it's bounded above this. Every m is bounded above by Qk minus 1 over 2 to the k, which is again constant because k is constant. And I'm claiming this whole sequence is bounded above by this constant sequence, qk minus 1 over 2 to the k. So, it may be obvious to you or not, but let's still prove it, because, I mean, we're like at least 40 minutes in, so why not? Shout out to everyone who's still watching. This is amazing. So we're almost done. So claim, I'm claiming that the sequence Rn is less than or equal to the sequence qk minus 1 over 2 to the k. Okay. And why? If not, then q to the k minus 1 over 2 to the k is less than Rn, which means that there is epsilon positive and capital N such that if n is bigger than or equal to capital N, then what do we know then? Rm on the one hand is bigger than qk minus 1 over 2 to the k plus epsilon. So that's by definition of Rn being bigger than this, but we've just shown by our value of k that this is less than qk minus 1 over 2 to the k. So then you get the contradiction essentially that qk is bigger than qk plus epsilon. And so this doesn't work. All right, so we have, this is true, right? So now we know that Rn is less than, so we know that Rn is less than or equal to this fixed value of q to the k, qk minus 1 over 2 to the k. But remember, Rn was an upper bound for S. So what we get is for all Sn in S, by definition of upper bound, Sn is less than or equal to R to the n, Rn is less than or equal to qk minus 1 over 2 to the k. But then, so, in other words, qk minus 1 over 2 to the k is an upper bound. For S. But that's a contradiction, because remember, how did we define qk? We defined it to be the smallest fraction with denominator 2 to the k, that is an upper bound, but now we found a smaller fraction of the form 1 over 2 to the k, that is an upper bound. Because you see, qk, this might be m over 2 to the k, so qk minus 1 over 2 to the k, that is m minus 1 over 2 to the k. So still a fraction with denominator 2 to the k. So in other words, qk minus 1 over 2 to the k is an even smaller upper bound. Then qk, and it literally contradicts the definition of qk bar. See, this is precisely why we chose the denominator as being 2 to the k. Not only this, but also for the geometric series. So that was very, very important. And therefore, I'm very happy to say that we are done. Therefore, what we have is that this Qn, this sequence, is the supremum of S. And therefore, any set, non-empty subset of R that is bounded above has a least upper bound. So in fact, this construction with Cauchy sequences makes R complete. Very good. And again, so I just want to remind you there are other constructions as well, decimal expansions or Dedekind cuts. Well, Dedekind cuts definitely make proving the least upper bound property easier, but this one makes proving the field axioms and everything much easier. So depends what you like more. All right, thank you so much. And again, if you like this and want to see more math, please make sure to subscribe to my channel. Thank you very much.